Hi, everybody. So I thought I would just do a few problems from the equivalence relations section to maybe help illustrate some of the ideas. So I'm going to do problems 3, 7, and 13 from section 11.3. So problem 3 says, suppose that you have a set with 5 elements, A, B, C, D, E, and suppose that you have an equivalence relation on it. And you know a few things about this equivalence relation. You know that there are 3 equivalence classes, and you know that A is related to D and B is related to C. And the problem is to write out R as a set. So remember, R as a set means you're going to be writing out R as a collection of ordered pairs in A cross A. And let's see what we know. We know that it's an equivalence relation. So we know, first of all, that R is reflexive. And reflexive means that all of the pairs, AA, BB, CC, DD, and EE, these all have to be in R. So maybe to be a little more careful, this has to be a subset of R because all of every element has to be related to itself. Now, we also know, because it's given in the problem, that AD is in R, and because of symmetry, it must also be the case that DA is in R, and similarly we know that BC is in R, so by symmetry CB is in R. Sorry, this should be, I don't know where I got this from. This should be DA. BC is in R, so CB is in R. So let's draw a picture of what we know so far. So here's A, B, C, D, E. A, B, C, D, E. We know each is related to itself by reflexivity. And we know that A and D are related. And we know that B and C are related. And so let's see where we are. So what are the equivalence classes at this point? Because that's the other piece of information that we have. We know it has 3 equivalence classes. Well, E, the equivalence class of E just consists of E, because the only thing that E is equivalent to so far is itself. And similarly, the equivalence class of A is the same as the equivalence class of D, and both of those consist of A and D, because A is equivalent to D and D is equivalent to A. And similarly, the equivalence class of B is equal to the equivalence class of C, which is B and C. So we actually have 3 equivalence classes at this point, namely the class of E, the class of A and D, and the class of B and C. And so we've satisfied all the conditions. And so altogether, R consists of AA, BB, CC, DD, EE, AD, DA, BC, and CB. Okay, let's look at another one. Here we define a relation R on the integers by saying that x is related to y if 3x minus 5y is even. So we're supposed to prove that it's an equivalence relation and to describe the equivalence classes. This is, I think, a nice exercise. So let's check the properties directly. So first of all, we have to check that R is reflexive. In other words, is x always related to x? And the test is xr is equivalent to x means that 3x minus 5x is even. But 3x minus 5x is minus 2x, which is clearly even because it's obviously divisible by 2. So R is reflexive. What about symmetric? Well, XRY, we have to check that XRY implies YRX. So XRY means that 3x minus 5y is even. What about YRX, which is 3y minus 5x even? Well, one way to check would be to take 3x minus 5y minus 3y minus 5x and see what we get. We get 3x, we get 8x minus 8y. So in other words, what we see here is that 3y minus 5x is 3x minus 5y plus 8y minus 8x. So if this is even, clearly this is even, so this is even. So we've shown here that that XRY implies YRX. What about transitivity? Well, now we need to know whether, let's see, XRY, suppose 3x minus 5y is even, and 3y minus 5z is even. We need to know that 3x minus 5z is even. And what I suggest we do is we write 3x minus 5y is 2k because it's even for some k, and 3y minus 5z is 2s for some s because it's even. And so 3x equals 2k plus 5y, and 5z equals 3y minus 2s, and therefore 3x, sorry, this should be z. Therefore, 3x minus 5z equals 2k plus 5y minus 3y plus 2s, which is 2y plus 2s plus 2k, which is clearly even. So if 3x minus 5y is even and 3y minus 5z is even, then 3x minus 5z is even, so x are z. So we've shown that it is an equivalence relation. Now, the other part is to describe the equivalence classes. And for that, we're going to need another piece of paper, or another piece of whatever you call this. So let me go down here to the bottom and add a page. Oh, I have a page. We'll go down here. So we have this equivalence relation, which says that x is related to y, provided that 3x minus 5y is even, and we want to know what the equivalence classes are. So let's just do some examples. So suppose x is 0. What is the equivalence class of 0? Well, it's the set of y such that 3 times 0 minus 5 times y is even, which is the collection of y such that 5 times y is even. But the only way 5 times y can be even is if y is even. So the equivalence class of 0 is just the collection of even integers. What about the equivalence class of 1? Well, The equivalence class of 1 is the collection of y such that 3 minus 5y is even. Now, if y were even, then 5y would be even and 3 minus 5y would be odd. If y were odd, then 5y would be odd and 3 minus 5y would be even. So this is actually the collection of odd integers. In other words, this relation is a very fancy way of testing for the same parity, namely x r y if and only if x and y have the same parity. And let's just check. So if x is even, let's do it this way. Even, odd, odd. Let's let this be x and this be y. So if x and y are both even, then 3x minus 5y is even, so they are related to one another. If x is even and y is odd, then 3x is even but 5y is odd, so 3x minus 5y is odd, so they're not related to one another. And it's symmetric, and the last case is if they're both odd, and if they're both odd, then 3x is odd and 5y is odd, and so the difference is even, so they are related. So from this little table, we see that, in fact, this relation is the same as asking if they're the same parity, and therefore the equivalence classes are the numbers which all have the same parity. So they're all either the even numbers or they're all the odd numbers. It's just a fancy way of doing even and odd. Okie dokie. Now let's do this problem, which is actually a tricky problem unless you look at it in the right way. So it says, suppose R is an equivalence relation on a finite set, and every equivalence class has the same cardinality. Express the number of elements in R in terms of the number of equivalence classes and the size of the set. So what's going on here? What's going on is that you have to think about what it means to have an equivalence class. So let's suppose we're in this situation. So we have A, and we take an element, choose an element in A. And let's look at its equivalence class. So remember what this is. It's the collection of pairs AM in R. Let's not use M because M is the number of equivalence classes. Let's use X such that AR, well, it's the collection of X's in R such that ARX, in other words, i.e. such that AX is in R. So if this equivalence class has M elements, that means that there are M X's that can go here, right? So if the number of elements in this equivalence class is M, then there are M elements you can put in the second position of an ordered pair in order to get an element of R. And this gives us a way actually to count the elements of R, because for each element of A, there are M elements X so that AX is in R. On the other hand, every element in R is of the form AX. So to make an element of R, the way you do it is you pick an element of A, and we use the multiplication principle. There are A choices for the first element, namely any element of A, and there are m choices for the second, namely any element of the equivalence class of A. So the total number is MA for the number of R. So this may seem a little magical, but I invite you, you could try to do some examples, except it quickly gets out of hand. But it's actually a nice application of the multiplication principle that we talked about in the last section.